Hello, IROS. I wish I could be here with you in person in the beautiful Kyoto, but this time I had to skip the conference for a very good reason. I hope you enjoyed the lecture. This is Professor Yael Rafaeli, a thoracic surgeon and my collaborator. She wants the best possible care for her patients, and she uses the most advanced technology to get this care. But there are still procedures that she cannot perform with surgical robots, that she has to perform openly, and she cannot abandon the see one, do one, teach one paradigm of surgical training. In robotic-assisted minimally invasive surgery, a surgeon controls a pair of robotic manipulators to control instruments inside the body of a patient. Now, over 1 million of these procedures are performed worldwide in a variety of applications, but still there are limitations. The force feedback is limited and training is still not optimized. Now, you may think that the best solution is to take the surgeon out of the loop completely and use the robots because of their advantage in precision and access to information. But the surgeon is really needed because of the ability to make decisions in arbitrary situations and because of their advantage in movement and manipulation. So if the surgeon stays in the loop, robotics and technology can provide assistance. It can provide augmentation. We can make sure that the surgical robot represents also the surgeon and improve the assessment and acquisition of skills. But to do all this, we need a model of the surgeon. Now, when I'm talking about a model of the surgeon, I'm talking about computational models that describe perception and action and how they change with development of skill. The field of computational sensorimotor control is the science of trying to describe how our brain controls movements and represents the external world with the help of mathematical equations. And even though every single one of us is unique and special, but we move in very stereotypic ways. For example, when I move from a point to a point, I make a straight path and a bell-shaped velocity trajectory. And when we make scribbling movements, our movements are characterized by the speed curvature power law. So we slow down when the movement is very curved near corners. When we are encountering a different change in the environment, a new mapping of our computer mouse is presented, or some device applies perturbing forces on us, we adapt these perturbations trial by trial. Now, all these findings were performed in laboratory environment and in overly simplified tasks. The question is, and this is what I'm going to talk with you about during this talk, is how you take the theories that were developed with these simple movements, like this point-to-point movement, into something that will be relevant for surgery, where you require interaction with tissue and the control of orientation and complicated movements. I will start with describing our work on surgical skill assessment and adaptation and skill acquisition in surgery that will describe the transition from these simple movements in the lab to something that is much more relevant to the kind of movements that you make in actual surgeries where you can help patients. And then I will circle back to describing fundamental studies that help us to develop experimentally validated models that can be used for solving challenging aspects of surgical robotics. So let's start with surgical skill assessment. You don't have to be a surgeon to really see that in these videos who is the expert surgeon and who is the novice. You can tell me which one you would like to perform a surgery on you. Today, surgical skill is assessed with the help of expert observation and questionnaires to try to make it standardized. But really, it is clear that the movement, the kinematics, contains information that can be helpful for automatic assessment of skill. For example, in other fields like sports sciences, the statistics of movements are analyzed all the time to try to infer something about the skill of the players. Ideally, we would like to do the same thing with surgeons. The first step that we did to come up with good metrics of surgical skill is to try to take classical experiments in motor control into the operating room. So we took a clinical robotic system. Here you see a participant in the experiment seated in front of the surgical console and controls instruments that controls a cursor on the screen that is placed on the surgical bed. And even in these simple point-to-point movement, we could clearly see the difference between novices and experts. Now, all of us are experts in making rich movements. So really, the only thing that our novices had to learn and what made their movements curved instead of straight is the dynamics of the master manipulator. The next step is going into the lab, and we use a surgical research platform, the Da Vinci Research Kit, that we owe to the Da Vinci Research community and the donation of the equipment from Intuitive Surgical. We can design tasks that are with increasing level of complexity to study movements and to try to come up with kinematic signatures of surgical skill. Such first task that we studied was the surgical needle insertion. So here the participant has to perform a movement from a point to a point, then drive the needle through the tissue and touch another point at the end. When observing the kinematics of the different movements of the expert and the surgeon, it is again clear who's the expert and the surgeon. Here in this plot, you see 10 movements from the beginning of the experiment and 10 movements from the end of the experiment. And already within the 80 movements performed throughout this experiment, some structure has emerged and the novices have improved. Of course, you can't be looking at this path to assess skill, and you have to come up with a number. So classical metrics like path length and time can help and really describe the improvement over the experiment. But the problem is that by looking at these metrics, at the end of these 80 trials, you can no longer distinguish between the expert and the novice, which clearly makes them not sufficient for describing skill.
Further in our search for kinematic signatures of skill, we looked at the control of orientations of instruments, because this control of orientation is really important in many tasks, including the needle driving, and the orientation data is readily available in surgical robotics. Yarden Sharon developed a metric that captures the rate of orientation change, and this metric was successful in differentiating between experts and novices even at the end of the 80 trials of movement. And especially important, this metric was successful in differentiating between experts and novices in the needle driving part and not in the transition part, highlighting the fact that the metrics should be tailored to the specific part of the procedure, and each segment or each gesture of the procedure may have different kinematic signatures. Finally, this metric was also successful in differentiating skill in the clinical-like dataset, and even here, this was successful to the level that it's really possible to develop a classifier between experts and novices based on a simple threshold. And one last thing that is important to remember is that we do not suggest that this metric should be used instead of any other kinematic metric, but instead we should look for many kinematic signatures of skill describing many aspects of the kinematics of movement.
So next, Yarden was curious whether fundamental laws that describe simple scribbling movements are also appearing in surgical movements that, as we mentioned before, are much more complex and require interaction with tissue and all that. She focused on the speed, curvature, torsion, power law that relates the speed of motion to how different from being straight the movement is and how different from being planar the movement is, the torsion. And indeed, she found that whenever the curvature and the torsion are high, we are turning or we are deviating from planarity, surgeons slow down. And this is describing very well the motion in the three different datasets. So the needle driving that I described before, the Jigsaw dataset that is publicly available, and even the clinical dataset. Now, what is more interesting is that the parameter of this power law, in this case the beta, the parameter, the exponent of the curvature, is actually a kinematic signature of skill. As you can see here, the relation between the beta and the global rating score that we mentioned before. Now, what is important is that this relation is at the global level, across different surgeons, and not in the local level of the different repetitions of the task by each surgeon. So really, this value of beta is a signature of skill that probably changes slowly with time and does not change a lot within several repetitions of the same task during the same bout of training. Now, for surgical movement, we already stated that the control of orientation is important. Or Tsuya, another student, has looked at the orientation control of instruments and actually found a new power law linking the angular speed to the geometry of tool tip orientation in surgical operation. So he used ring transfer task, but also needle driving task, and found a relation between the angular speed and the local curvature. He will be presenting this paper tomorrow. So far, I talked about skill acquisition and how can we assess skill. But in the study of computational motor control, there are separate addressing of adaptation and skill acquisition. And adaptation is restoring of previous performance in face of perturbations and disturbances and changing environments. Now, adaptation is also very important in surgical skill. And why? For example, this is, again, a procedure that is performed by Yael, the thoracic surgeon, and this is done in close proximity to the heart. She operates on the lungs. This periodic movement of the heart actually pushes her instruments and changes what she's looking at. So there is this periodic movement and periodic forces that she has to cope with. Well, I asked her whether this is indeed challenging, and what she says is that it only bothers me in suturing, where movement is delicate. For the larger movements, you just adapt to it without paying attention. So we took this, you adapt to it without paying attention, and we wanted to take it to the lab and studied whether indeed you're capable of adapting to periodic forces and to periodic movements that perturb your motion. So here we have a user seated in front of the robotic console, and we designed two separate perturbations. One of them is a force perturbation. The task is a pattern cutting task that is often used in surgical training, where the trainee has to cut along the circle on the gauze without deviating from the painted circle. In this version of the force perturbation, we actually apply forces on the master manipulators, on the manipulators that they hold in their hands, that push them away or inside in the radial direction of the cutting of the circle. So we have a very clear separation in the dimensions of the task between the perturbation and the movement itself and the plane where they're performing the cutting. And there are very different ways that they can cope with the perturbation. They can try to model the forces and counterbalance them. They can try to time the cutting. They can stiffen their arm. There are different ways to cope with this perturbation. The other kind of the same perturbation but is different is the movement of the platform. So this is more similar to what happens in the real life, the movement of the heart. Here we take the pattern cutting rig and we move it with a Stewart platform. So to quantify the performance, we're interested in the trade-off between the time it takes to perform the procedure and the accuracy, and essentially the improvement in the speed-accuracy trade-off. In the top plots, we're looking at the force perturbation experiments, and in the lower plots, in the movement experiments. So we see that they improve in the baseline when they are not exposed to the perturbation. Then when they're exposed to the perturbation, they keep improving, both those who were exposed to the perturbation and those who were not. And when they are returning to performing the pattern cut without the perturbation, what was quite surprising is that they reach the same performance. This means that first, the fact that they trained with the perturbation did not hurt their performance without the perturbation, which is good news. It means that you can incorporate complex training, including perturbing forces and periodic forces, in training without impeding the training process. But the bad news are that, in fact, it means that they did not form an internal representation of this perturbation. And it's questionable how well they will be able to generalize to conditions that are similar to this periodic perturbation but slightly different. And indeed, when we tested this generalization, either back to the same perturbation or to unpredictable perturbation, there was only slight and not significant advantage to the group that learned the perturbing forces, and significant but still small advantage to the ones who learned the perturbing movement platform. The next thing I wanted to say is that we have to remember that as we move from the lab to the real life, we move to much more complicated data sets. It means that the procedure, instead of being something that can be completed in a few seconds or maybe in a minute, when we go to the actual procedures, the clinical procedures, we're talking about even hours of data for a single procedure, which means that we have to be able to use machine learning to help to make sense of this data and to deal with it and parse it into smaller segments. So in this direction, I want to share our attempt to generalize a deep learning algorithm that is trained for gesture classification, so separating a larger movement into smaller components from dry lab data to clinical data. And in fact, this is not a very easy task because models that generalize well from between two different parts of a structured dry lab data set do not generalize well into clinical data, even if you apply different augmentations, like the augmentation that we tried here, which is adding rotated versions of the data. that is really helpful to generalize to other dry lab data set, but not to clinical data. And the only thing that we were able to help to actually generalize into clinical data is to train the algorithm that we determined its architecture from the dry lab data, but train it on the actual clinical data. The next thing we wanted to see is whether we can predict the timing of camera movements from kinematics. And here, why is that important? Surgeons in robot-assisted minimally invasive surgery have to use the same joysticks to control the instruments and then switch to control the camera. Now, of course, this is time-consuming, and ideally, we would like to be able to develop an autonomous controller for the camera. Here, Hannah Kosowski tried to make the progress toward developing such autonomous controller for the camera by predicting the movement of the camera from the kinematics. I want to highlight we are not using the video data to predict the movement of the camera, but we think that there is useful information for predicting when the surgeon is about to move the camera in the actual movements of the instruments. So she trained an ensemble of networks that took segments of the movements of the instruments that were before and not before the camera and tried to predict whether a camera event is going to happen. And we were really happy to see that indeed she was able to reach accuracy of over 70% in predicting when a camera is going to happen from just 1 second of kinematic information before the actual camera movement. So in the last part of the lecture, I would like to go back to more fundamental and basic studies that are not by themselves relevant to surgery, but their conclusions are really important to address questions that are needed for surgery. The first is the delay. If you were to operate from a distance, which is quite easy to extend robot-assisted minimally invasive surgery to remote robot-assisted minimally invasive surgery, your brain has to cope with delayed feedback, information that arrives not simultaneously with your movements. We studied the question of how the brain copes with delay over several years in several contexts. First, perception of stiffness, which is really important for surgery because the surgeons have to understand what is the stiffness of the tissue during performance of procedures. We present participants with virtual reality and with simple robotic devices and ask them to interact with objects and answer which of the pair of two objects has higher level of stiffness. And we infer from this information how delay affects their perception. And for example, we found that when the force information is delayed, they perceive the object as being softer, and the way to what extent they're softer depends on how they interact with the object and with which part of the arm. But in the same time, they adjust the grasping forces in anticipation of the forces that are going to be acting on them and with the correct estimation of stiffness, but also with the correct timing. So in the same time, the brain, on one hand, copes with the delay and represents it to time the movement properly, but in the same time, the perception of stiffness is biased. Well, in state-of-the-art systems for surgery, still force feedback is not existing. But even if just the visual information is delayed, this can affect your motion. For example, in this study of a modified game of Pong, where participants adapted to a delay between their movement and movement of the paddle, we found out that once exposed with this delay, participants improve. But if after this improvement, they are asked to perform simple reach movement, they overreach. This is something that is really important because if surgeons adapt to delayed visual information by overreaching and making their movements larger, this can make them miss important target tissue that they're trying to reach in their case. And if modeled properly, we can compensate for that with the surgical robot. Another important challenge is the missing force feedback in robot-assisted surgery. Now, the reasons are technical, both in the sensing of the force and in the difficulties of providing the force feedback due to stability and transparency consideration. But even more so, there is currently disagreement on whether force feedback is at all useful in surgery. So we try to study whether force feedback improves performance in surgical needle driving. And we thought that the reason for this agreement was that we just didn't look hard enough at the advantage. But no matter how hard we try to quantify the performance in the needle driving with different metrics that we developed, looking at the forces and at the movement and all the metrics of skill that we can develop, we actually didn't find advantage to force feedback. So now we think it's actually related to the fact that either the force feedback that we provided was just not good enough, or maybe the task of surgical needle driving through soft tissue is just easy enough to perform without force feedback due to the visual information of the tissue. So going forward in the direction of improving the force feedback, what is very promising in these days in the haptics community is providing users with information that is tactile, that is providing information on the skin instead of actually applying force feedback. And the tactile stimulation, especially with stretching the skin of the fingertips, was described over the years to be successful in many, many tasks. For the substitution of stiffness information, friction, for guidance, for improving accuracy in tasks. And in the lab, we tried to develop computational models that will describe how actually the skin stretch information is affecting both the perception and action. The way we address this question is, again, going back to very basic experiments in interaction with elastic objects. So again, we ask participants to perform movements, probing movements into the elastic object and apply stretch stimulation on their fingertips or not. By comparing pair of objects and using psychometric curves, we can infer the augmenting effect of the stretch of the fingertips on the perceived stiffness. And we actually found that stretching the skin of the fingertips causes an immediate illusion of touching a harder spring. So it is enough to touch the object even once to experience the illusion. And in the same time, when we're looking at the grasping forces, we see that the grasping forces become stronger and stronger with each repeated interaction with the elastic object due to the stretch, which means that they slowly and gradually form an internal representation also of touching a harder object. And these two effects on the perception and the action are actually separate, and there are two separate processes. So as we go about designing the controllers, we have to take into account the perceptual effects and the effect on action separately. Further exploring this illusion, we actually found that this illusion of touching a harder object is robust to noise, but weakened by the presence of visual information. I started this talk with saying that we need a model of the surgeon. But in fact, if you take together everything that I told you during this lecture, we actually lead to the conclusion that one model is not enough. And we actually need several models that describe separately the perception, the action, the adaptation, the skill acquisition. And the sensorimotor system of the surgeon is too complicated to describe with just one unifying overarching model. And the challenge is how you are taking these separate models that are relevant in each of the contexts and use them in order to improve all these different aspects of a system to the surgeon that I started with. The key is identifying within each of these additions that we can add from the surgical robots to the user and use the appropriate models. So it's a task of matching between the proper level of description of what the brain of the user is doing to control the motion and process information and the augmentation that you want to apply, whether it's force feedback or assistance, or if you're trying to develop a new training algorithm. Each of them would require their own model. So the last thing is thank you to the team who actually did all the work that I just told you about, and thank you for listening, and I'm open for questions.